Thank you everyone for joining us on this webinar this morning. My name is Vikram and I work for GL Communications. I am joined on this webinar with my colleague Sanjeev Jigajini, who is based out of our Bangalore, India office. This webinar is on our ability to capture, decode, and analyze 4G and 5G protocols of these next generation networks. We have a lot of capability that we are excited to talk to you about with regards to 4G and 5G protocol analysis and data capture and so forth. So I think a lot of you are familiar with GL Communications, but for those of you who are not, we are located just outside of Washington, D.C. We've been around for over 35 years. We are a consulting company. We do a lot of telecommunications consulting services, and we also build test and measurement equipment. We build test and measurement equipment for all different types of networks, whether it's analog, T1, E1, Ethernet, fiber optic networks, wireless networks, land mobile radio, cellular, all these different networks. We build hardware to test these networks. And you'll learn a little bit more about it in this webinar. Our solutions focus on analyzing these networks, monitoring them, visualizing the traffic flows, capturing traffic and long-term storage. We can also emulate traffic going over these networks. So that's a little bit about us. Our customers include basically everyone. Telecom service providers, internet service providers, equipment manufacturers, government agencies, government contractors, and so forth. Basically, anybody who's interested in telecommunications has come and talked to us and has bought our solutions over the years. We want to talk to you today about 4G and 5G testing. So what are the types of requirements that people have when they come to us for 4G and 5G testing? Well, first off, performance of these networks. What is the latency over these networks? What what is the reliability of these networks? What type of data rates and throughputs can we achieve on these networks? And so forth. So another thing is protocol validation. Customers are always building new applications and new infrastructure, and those applications and infrastructure have to be able to handle the appropriate protocols. So customers want to know, okay, is my device under test handling different protocols appropriately? Is it generating the protocols appropriately? Is it responding to the protocols appropriately, and so forth? You also, a lot of customers want to know how their services or their devices or their infrastructure behave when subject to network impairments. So in this scenario, they would want us to emulate network impairments, things like reduced bandwidth, packet loss, delay, bit errors, and so forth. A lot of customers are interested in voice quality testing. For those of you who are familiar with us, we do a lot of voice quality testing. And we can do voice quality testing over any network. But specifically for 4G and 5G, we can place and answer calls, we can send audio files, we can measure the voice quality, all using the latest industry standard algorithms, and so forth. Okay, so service-based interface architecture. So you know that these 5G networks, a lot of the infrastructure is virtualized. A lot of the infrastructure is in the cloud. Nodes can be activated and deactivated and spun up and taken down dynamically as virtual machines in the cloud. So a lot of customers want to test that capability, and we can help them with that. A lot of customers want to test the backhaul. So whether it's a 4G or a 5G network, eventually the traffic has to hit the backhaul. And when we talk about the backhaul, we mean the wired networks that are transmitting at very high data rates, all the traffic between the cell towers and so forth. Those can be those data rates can be up to 100 gigabits per second or even higher. And so a lot of customers want to monitor and capture traffic over the backhaul. And finally, customers want to know about deployment and scalability of these networks, bringing new nodes online, taking nodes down, and so forth. And they come to us and ask about that. Okay, so we make very sophisticated hardware and software for testing 4G and 5G networks. One of our best-selling products is called PacketScan. We'll talk about it more on the next slide. But here, what I want to mention is that it's a PC-based solution. Depending on what data rates you're trying to capture at, depending on how much storage you need, depending on whether you need a portable or a rack mount form factor, we can build the platform for you. For example, if you need a high performance machine but you need it to be portable, we can build a high performance machine that is basically a lunchbox PC that you can put in a Pelican case and carry around with you. We put specialized network interface cards into this lunchbox PC. We put our proprietary software, PacketScan software, on it. We customize the RAM and the storage. We customize the cooling. We've optimized the cooling to make this a very durable solution that can run indefinitely, days, weeks, months on end, without overheating, without crashing, without any interruption. So we have different form factors for both portable and rack mount scenarios. If you just need a lightweight installation that you can just carry with you very conveniently, we also just sell a pure software-based PacketScan software that you can install on your own notebook PC. So, and I want to mention we can customize the number of ports. Some customers only need 1 port. Some customers need 2. Some customers need 8 ports. So we can customize a number of Ethernet ports on these systems. Okay, so we have designed a very powerful protocol analysis software, which we call PacketScan. PacketScan can analyze many different protocols on 4G and 5G networks. Actually, beyond 4G and 5G, it can analyze basically any sort of packet-based protocols. So the way it works is that the software is deployed on our hardware, and you would connect it into the monitor port on a switch, somewhere where it can basically capture traffic from these networks. And once it's capturing that traffic from the monitor port on a switch, you simply invoke the software and you get full details on all the traffic that's being captured. It will all the way down to like the binary data and all the way up to call detail records. So it can intelligently group the packets together, build call detail records, save calls, play back calls, perform voice quality measurements, wave diagrams, packet-based calculations, packet loss, jitter, stuff like that. So PacketScan is is a very powerful, very flexible tool. These are just some of the protocols that it can support. So legacy protocols like SIGTRAN, it can support that. It can support VoIP with SIP and RTP. It can support 4G, 5G, and so forth. So that's the PacketScan solution. Moving on, let's now talk specifically about 5G. So 5G, there's a lot of different elements in the 5G core network. So here we're just showing some of the interfaces that are are present on a 5G network. And the key is that PacketScan can actually decode all of these different interfaces on the 5G network. And again, it's the same kind of configuration. You would plug it into a monitor port on a switch. As you know, 5G 5G is all packet-based, really, when it hits the core network. So you can get all the traffic straight from the Ethernet switch and send it into the PacketScan system. The way we license it is we license the whole 5G protocol suite, and you get all of the different interfaces that come with it. So it's important to note we tap in at a wired interface to capture 5G traffic. So we don't grab it from the RF. We grab it from the wired interface. If you have any sort of encryption going over these 5G networks, and if you have the encryption keys, then we can also decrypt the traffic so that you can analyze the unencrypted traffic as well. So this is how we do 5G core network protocol analysis. Okay, so my colleague Sanjeev Jigajini will walk through the next few screenshots with you, and he will talk. This is the PacketScan software, and he'll talk about the types of things that you can do specifically for 5G with PacketScan. Sanjeev, feel free to start.
Yeah, thank you, Vikram. Yeah. So here is our main PacketScan main window. This framework is common for any of the protocol analysis like 4G, 5G, or all our SIP protocols. So here in this main window, when we capture either real time or load any of the offline trace, in this main window we try to display all the frames and their decode summary, like for example when the packet has been captured and what is the length of the packet and what is the IP address and what is the transport protocol. All these informations will be displayed in the summary tab. As you can see here, for each of the frames we have these like decode important field parameters, and when we select a particular frame, you could see that complete detail of that particular selected frames, right from beginning, like MAC address, IP layer, transport layer. And here is an example which we are trying to show the NGAP layer, like which is our N1 N2 layer, which is between GNB and the AMF, those messages which are the binary interface. So here you can see that we are decoding that NGAP layer, and we display all the IEs. In the similar way, we have this NAS layer decode also. When it is plain text, we'll be decoding, and if it is encrypted, and we decrypt based on the credentials, and we display that NAS layer also. So this window is all about the frame by frame details, wherein they can look into particular frames and understand what is there in that frame, and look into more details of each fields in that frame. So this is our main under window within that application or module, which we call it as a packet data analyzer summary view. So here you can see like whatever the frames which we have captured. Here we try to decode them and bind them in terms of call detail records, like all the related messages we bind, process them, and extract the important parameters, and displays those statistics. And you could see that we display in terms of CDRs. So like if multiple users are trying to attach to a network, so you will be seeing the CDR with respect to each users here. So you can see that for a given user, you can see the start time, end time, what is the duration, what is the SUPI, SUSI, and if a TIMC is allocated, what is the STIMC, and what is the IP address of all these important parameters which are present in those messages has been extracted and produced as a call detail records. And when we select a particular call, you can see that ladder diagram. You can see here, it will help you to understand the entire message transaction happened for that procedure. And even between across interfaces, if we have provided the capture which contains the all the interfaces messages, then we bind the messages which has traversed across the interfaces for that particular UV activity. So you could see here is an example, like when a particular assume like when a user switch on, even he tries to register to the network, this first message will be exchanged between the G node B and the AMF. Okay, access and mobility function. So you could see here the first he tries to register with his information. Then when he tries to register those like for the given UV, he tries to authenticate using his the another EOSF function, so which is again between different interface. But when we try to display here, we show it as a for a UV activity, we club them from the different interface and we try to show them, so which helps to understand what has happened across the interfaces also. So you could see here, once he request, again that AMF will contact UASF and ask him for the whether the requested UE is authenticated or provide his information. And then that interface will try to access UDM. For example, UDM is our database. All the our subscription data, security information, everything will be stored in UDM, which is equivalent to your HSS in case of LTE. So all these informations will be stored. Again, USF will try to contact the UDM and get the credentials. So then again, those credentials are forwarded to the AMF, and AMF will try to authenticate the UV through the GNB. So these internal messages which are exchanged between the interfaces, you can correlate them, and with this you will be able to see entire transactions. Same way, you can see that security mode has been exchanged and it is authenticated, and once it is attached and accept has happened, then it tries to create the get the information, and it tries to create the sessions, data sessions like IM for any of IMS or the internet, all these messages. So this window or this display helps you to understand what is happening for that particular UV, and you can understand. And when you click on a particular message, you can also see the right hand side, the entire details of that message. So similarly, we can see even the individual interfaces also. There are a lot of interfaces in the 5G core network, and we can show them as end to end, or if we are want to monitor or look into that all the transactions which has happened between particular interface, then we can select here. We have a drop down to select the interfaces. Then if you see here, N12 is been shown here, which is between AMF and USF, which is used for mainly authentication. So all the messages exchanged between those two nodes, again we bind based on the session ID, and we try to show them as like request and response. You can see here, this is a JSON content, which is actually over the HTTP message, which is carrying the JSON contents, where we decode this JSON part, and we try to show that important parameters. Like you can see here, what is the method, post, and then what is the function name, and all the and the JSON content, what it wants, and what is the security. So these information which helps you to look into that particular interface transactions. So this is an example of N12. Similarly, so this is an example for the N13, which is between the AUSF and UDM. So here we are showing that we can decode independent interface and show them as a separate CDRs when we are interested in looking into only between two nodes. So similarly, so these are all like same, but we are showing here what all the interfaces we cover and what are those important parameters we take. So here you can see that N4 interface between like this is SMF and UPF, which is mainly for this establishing the session, data session, and that control transaction. You can see here that PFCP messages has been exchanged between the SMF and the UPF, which is a session management function, and the user plane function transactions. So you can see that all the important QFI and what is a UPF TID, what is a tunnel IP address, all those important parameters we extract and provide them as a call detail records. So this is an example of N8 interface, which is in between this AMF and the UDM, and it tries to fetch for any of the important informations with respect to the particular UV. AMF will be contacting directly the UDM, which is a database of all the users subscription, like it stores all the subscribers complete information in the UDM. When the AMF requires any of the important parameters respect to particular user, he will contact UDM using this interface. So this is an example of end-time. So here we are trying to show like we cover most of the interfaces, and also we show them as a per interface messages, which help you to concentrate on particular messages. So it is an example of between SMF and UDM. Whenever the session it wants to create a session and get the information about this like subscription, so those information will be fetched, and it will be used by the SMF. So this is an example of N11, again N11, which is AMF and SMF this interface.
Okay, thank you, Sanjeev. So now let's talk about 4G. We still have a lot of customers asking about 4G analysis. So the concept is the same. The PacketScan still connects into a monitor port on a switch, and it basically captures traffic from all these different interfaces on the 4G network. Again, we license it for the whole 4G protocol suite, so you can capture and monitor all of the various core network protocols in 4G with the PacketScan software. Again, it's a wired connection. We don't capture off the RF. We captured at a wired interface. But it's the same software, just like for 5G. A lot of the screenshots that you're about to see for 4G look similar for 5G. It's the same user interface, same everything. You can do basically the same type of stuff. You can see call detail records, signaling events, and packet measurements, packet statistics, and so forth. You can save the calls, play back the calls, save the call detail records, drill down to specific packets, even go all the way down to the bit level. So that's a little bit about that's a high-level summary of our 4G analysis. Sanjeev, you can walk through some of these screenshots for 4G with PacketScan.
Sure. So as you saw in the previous slide, So like we analyze even the 4G also. So with respect to 5G, similar to that, we have this same framework wherein we display this in the main window. We display all these message details of each message, and when a particular message is selected, we'll be providing a decode of that. Here you could see that we provide the like SNAP decode, which is of this LTE SNAP message, which is between eNode B and the MME. So we decode all this information, means provide the details of each message. You can see here that it is an initiating message which carries this within that NAS PDU and the other informations. So similar to 5G, our framework is same. So when we have this LTE messages, we again we bind them based on the UV identity and all the node important session parameters. We show them into messages which are between across interfaces. We bind them for a given UV, and we show them as a complete call detail records, and also the related messages here. So our important main feature is like you can see here, whenever in the LTE or in 5G, whenever a message is initiated, for example, first time user attaches, he starts with the UV identity, and the authentication happens, and he will be authenticated. And once the authentication has happened, so from there onwards, all the messages which are related to the UV will be encrypted. So which will be encrypted, which will not be able to decipher. So in order to decipher that, once we get this authentication information, we learn the security exchanges, and we store in our application. So that whenever the next messages, which is a ciphered message which is received between from the eNode B to MMB, we use the whatever the security context which we have learned from the S6A, or the which is between MME and HSS. We have learned this, and we use this information to decipher, and we show that deciphered messages for this NAS layer, uplink NAS layer. So this is our main feature. Also, as you are aware, like apart from attach procedures, we do have the, whenever a particular EV moves from different location, there will be handovers happening between. It can be handover, can be intra MME handover or inter MME handover. So whenever handover happens, they will may not be again doing the authentication. So they will simply exchange the information, since the MME or Node B will be having those authentication context information. So again, there won't be any exchange of the security parameters. But since we have learned those messages, we even decipher the all the messages when after this handover, all these handover messages, and we start displaying the NAS content. So we even handle the handover messages which are exchanged for the intra or inter MME, and maintain the security context to decipher these NAS layers. And also, whenever the UV go into ideal mode, and when it comes back to the again, it tries to connect to the network, we try to bind them. When it connects back to the network, it may not again authenticate, so it will use the previous allocated TIMC and continue to send the messages in a ciphered format. So even we decode those ciphered messages based on the security information we had processed previously, and extract the important information, and uh, produce them into a CDRs. So it is same in case of 5G and 4G also. So we learn the credentials as and when we progress, and we use that credentials to decipher these messages. and we provide all the extracted important parameters, which we can even send to our database, which will be explained in the next slide.
Okay, thank you, Sanjeev. So again, I want to now talk about IMS monitoring. Just like before, we connect the PacketScan platform to a monitor port on a switch, and we can analyze all these different interfaces, SIP, S13, CX, DX, and so forth. If you have the encryption keys, we can also decrypt the voice over LTE and voice over new radio calls if they're running over IPsec. So again, just like before, when we license PacketScan, IMS protocol analysis is a optional license, and you can just simply add it, and you'll be able to decode the IMS protocols. And now Sanjeev will show you some screenshots related to IMS.
So you saw in the previous slide that IMS is the important component in 4G and 5G. So we even support the monitoring of that IMS network. So you can see here, so same like framework, which will handle this IMS like SIP messages also. So when you see the CDRs or call detail records, what we decode those SIP messages that can be carried over, like it can be carried over TCP or it can be over UDP. So we support TCP, UDP, and it can be over IPv4 or IPv6. So we support IPv4 v6, and which is carried over. It can be carried over TCP and UDP. So here is an example wherein UV is trying to make a call, and this passes over this serving control function, so which is a part of this IMS network. So invite message has been sent, and that control function will then forward that invite message to the intended UV, and those messages you are able to see here when we are capturing this in the IMS network. And we produce the when we select a particular message, again we produce this entire details of that message, wherein they can try to look into a particular fields, like what is the call ID, or what is the from to tag, and any all other informations for a particular selected message. And in the CDR, we provide all this information, signaling and audio informations, like signaling, like who is the caller, callee, when the call has been started, and if there are any error codes, if any failure in the call, then we extract the error codes from that message transactions, and we try to show them. And if it is a established call, then there will be exchange of audio. We bind that audio to a like particular CDR, and we even calculate the voice quality, which we rate them using this MOS score and R factor. So we learn those. That means we bind all the RTP and provide this score for that RTP, whether that RTP exchanger RTP is having a proper quality, or if there are any issues, we even show like measurement, like parameters, like missing frames, out of sequence, or if any delay we have experienced any delay, then we provide those parameters, which helps in understanding what has went wrong in the call. Like it can be because there are a lot of missing frames might have happened, or there could be a delay in reaching the packets due to some network congestions. I may having a lot of delay experienced. So all these we use these timestamp parameters, and means produce this CDS, which helps you to understand the complete details for a given call. So along with those call detail records, when we come to IMS network or any of this one, we want to understand what is happening in that network at a like broader way. Like we want to know, understand how many registration attempts has been happened, and whether those all the registration happened were successful, or we are seeing any of unsuccessful registrations. So we provide the important key performance indicators. For example, you can see here the registration versus deregistration. So how many like registration and deregistration attempt has happened? Out of them, how many registration has been passed and how many have been failed over a time? So this graphical represent helps you to narrow down the to the timeline wherein when you have experienced like some invalid scenarios or some issue in the network. So this graph will help you. Such KPIs will help you to narrow down to a particular timeline or the particular event, and we can go and look into that details further. So these graphs will help you to look into that the overall performance of the network. So this is one of the key KPI which we produce, and we provide a lot of other KPIs also, like means how you can see in the next slide. For example, here you could see that if there are any failures in the call attempts or registration attempts, so we show this graph wherein you can just understand in the network what are the different kind of errors and happened in that network. So you can see here we categorize them into different errors, and in this graph we are trying to show what are the top 10 failure causes for the, like we can, there could be a lot of failure causes, but here we try to concentrate first top 10, so which we can be addressed or which can be quickly look into those kind of category of errors. So you could see here, like we could see that we provide in terms of percentage also, like how many total error codes, out of which how many are like because of the network failure or the user failure or any of the global failures. So these KPIs are very important in order to understand the overall network performance.
Okay, thank you, Sanjeev. So I want to introduce one other component to our solution. It's called Net Surveyor Web. This is a web-based dashboard, and what it is a we supply it on a server-grade PC with a back-end database, and it can take data from multiple PacketScan systems deployed on your network, and it can save the data, such as the call detail records and voice recordings and so forth. It'll save the data in the database, and then it'll present a very user-friendly web-based interface where you can view all of the data. So in terms of scalability, let's say you're monitoring a big network with multiple packet scans deployed throughout the network, capturing traffic from multiple locations. You want to be able to take all of that data and send it to a central location. And that's what this Net Surveyor Web system does. Because it is browser-based, you can log into it from anywhere. Multiple users can browse to it and view all the information. So Net Surveyor Web is a very nice addition to our testing tools because it allows for scalability. It takes in data from multiple PacketScan probes and presents it in a very user-friendly fashion. We can customize the data, customize the storage. So if you want to do long-term storage of hundreds of thousands of or millions of calls, we can increase the storage as needed. So that is Net Surveyor Web. It just has to be on a network where it can receive data from the PacketScan system. So they just have to be able to communicate via TCP/IP. Whoops. So like I said, it's a web-based dashboard, and it'll take all the call detail records, and it'll list them very nicely for you in a table. And in any one of these calls, you can click on it and get more information on the call. You can also quickly view specific types of calls: all calls, failed calls, past calls, things like that. You can define your own key performance indicators and view those. You'll see some graphs on the next page. And of course, we can monitor over different protocols. So we can monitor over 5G, 4G, and VoIP, and all these other protocols. You can just click from a drop down to sort on that protocol. Historical storage. So you can specify, where, what day you want to pull up records from, or all the records last 30 days, blah blah blah. You can filter on the data as you wish. Remember, it's going to be a huge amount of data that you're capturing from the network. So having these filters is very important. So let me go to the next slide. Here's another look at the LTE calls specifically. So for every LTE call, you get the full call detail record. You get the call duration, the start time, calling number, called number. You can basically scroll right here and you get all sorts of different information, user IDs, and things like that. For any call, you can click on it. You can see the whole call setup, the whole call flow, all the messaging, all the signaling, and so forth. Here are some other key performance indicators that customers ask about. They're on the screen here. In the interest of time, I'm going to kind of speed up here, but you can define your own key performance indicators. But here are some of them that come by default with the program. You can also make graphs of all these different types of events. So you can graph the total number of calls over a given time period, and then what type of calls these were, what events happened in these calls, things like that. So here we're looking at causes and session failures, why something failed, what was the reason for the failure, and so forth. You can download all the data. You can save it as PCAP files if you wish. You have easy access to all the data. And you can play back the call straight from the user interface. So you can save that call. You can play it straight from the user interface. You get both sides of the call. You get all the information. Again, calling number, call duration, mean opinion score for voice quality, codecs, and things like that. So, and finally, you can export everything to PDF, to CSV files, and so forth, and really get a nice report of your overall network. On a daily basis, hourly basis, whatever you want to do, you can automate it so that it automatically puts out these reports at a given time interval. All that type of stuff is doable. Okay, so thank you all very, very much for attending this webinar. Please feel free to contact us at info@gl.com. And if you haven't already, please subscribe to our newsletter. Thank you.